Hello. Hello. Today, we will be learning about graphs and tables. So we will look at an in-depth analysis of looking at graphs and charts. So you'll learn what graphs and tables are, the different types of graphs and tables, interpreting graphs and tables, and some function graphs that we will look at the end. So let's get started. So what are graphs and tables? A graph or table is a pictorial representation or diagram that depicts data or values in a clear, neat manner. So that's an example over to the right, right? There are an assortment of these school supplies in that top picture, all chaotic looking. However, the bottom shows a table organizing those types of school supplies and the number of the school supplies just to simplify it to make it look more clear, to more neat, more visually appealing as well, uh, and more easy just to find that information or find that data. So what's a table? A table is information shown in rows and columns, right? And that's an example of a table down below. Question, the question type, um, average, number of women who answered, number of men, their yes or no's to each. And that just shows the percentages as the data. If we need to uh, take away some information, but right, we'll look at those rows. We'll look at the cells, columns, rows in a second. So why people use graphs? Graphs are used to compare the amount of objects or numbers. They're simplified and easy to interpret, and that's the most important part. They're simplified and easy. They're easy to understand. It's easier to get information out of it, and it looks more professional, right? And that's why where they're most commonly used. They're used in experiments in labs to organize hypotheses, to organize your conclusions. Research, you have so much data, thousands of data entries, and this simplifies and so it's not so chaotic. Business corporations, statistics, collecting data, comparisons, contrasts, and surveys. For surveys, it would be using, you can see it would be asking questions and the percentage of people who answered yes or no and their responses. So let's look at the key parts of graphs and tables. So the title, right? This is the most important part, one of the most important parts of a graph. And the title is normally at the top of the graph. It doesn't have to be at the top, but it's traditionally at the top. Uh, if if it looks like a traditional graph, where the data is going from left to right, then it'll be at the top in a horizontal fashion, so it'll be like straight above the top. Now, this graph could be tilted sideways, tilted, you know, 180 degrees, and then it would be sort of vertical in direction. But that's a little bit more rare, I'd say. And what the title does is it provides a short summary of typically a few words to describe the graph. This helps the readers to understand what the graph is about, right? And we can look at the title right now, Olympic Games winning times. And from that, we know what the data will tell us. We know the data will tell us, the either, we know it's the year and we know the time. So we can just see that and we can really just understand what that graph will tell us, right? We know the distance isn't changing, so it's just the years are changing and the time is changing, and we can see that from the graph now, the years by time. So really, that title just gives us that summary of what that graph is going to be about. That quick summary, the readers are already just diving into what they need to know, right? And that would be that title right there, Olympic Games winning times. And that's the more important title. Not I won't say important, but that's the more important piece of the title, Olympic Games winning times. But track and field and men's 15-meter run is sort of like a subtitle to that title, right? A little bit more information to help us understand what's going on. Um, to help us understand that this is the track and field, to understand that this is the men's race, then it's the 1500 run, a little more specific. So let's look at the source, right? The source tells the readers where the information came from, where it originated. This part is only necessary if the data does not come from your own work. So, for instance, if I take information from, let's say, some other website and I use it in my own conclusion, well, I can't just say that data is my own, right? That'd be plagiarism. What we would have to do instead is just cite it, and you can put that site in the fine print in the bottom, which is what I did, which is what this chart did. The highest level of education. This came from the U.S. Department of Labor, Bureau of Labor Statistics, Office of Employment and Unemployment Statistics, Current Population Survey, CPS 2004. Right. That I did not come up with this data points on my own. I took it from some other place. If I take it from some other place, I just have to cite it, right? You've probably already learned that with plagiarism, and it's the same idea with charts and graphs. We can't plagiarize, so we just need to give credit where credit is due. However, if the data is your own, right? Let's say we're doing an experiment and we're measuring certain data points, right? That would be okay not to have a site, right? Because it's your own data, it's your own experiment, and it's your own result. So that's perfectly okay not to cite anything there. Right. So what's the key slash legend? You'll hear either term. They mean the same thing, and they explain what the data corresponds to in the graph. Right. So right here, the legend would be over to the left. That it explains. No. So normally this graph is a little more in depth because it says orange without looking at that key. It says orange, plums are green, pears are light blue, apples are dark blue. Normally, it will not say that if it gave that legend, but and those fruits would then correspond to each color. So it just helps you understand what color that fruit would be talking about. So the x-axis. Traditionally, the x-axis goes horizontal for graphs. The x-axis normally shows an independent variable. What's the independent variable? The independent variable is a variable not measured. So if we look at the x-axis here, we can see that the x-axis is the year, 1998, 1999, and 2000. And traditionally, it'll go left. If the graph is going horizontal, it will go, at the bottom, also horizontal. If the graph is rotated 180 degrees, then it will go vertical. And it will take the place of that y-axis we'll talk about in 1 second. Right. So this x-axis just tells us the year right here, right? Those 3 years that we are measuring who uses the internet in that percent of age groups. We can also see that key over to the bottom, over to the right, right? We if you don't, you won't know what the orange, red, blue, green, bars stand for. However, that legend or key tells you what those specific numbers correspond to. I mean, specific colors correspond to, so you can understand that. The y-axis now traditionally goes vertical for graphs. The y-axis normally shows the dependent variable, which is the variable that is measured. So what is the y-axis here? Well, the y-axis is the number of students, right? So the x-axis here would be the levels, right? And we can even see, the title being letter identification. Then we have the legend, right? The difference of blue and red. Excuse me, green and red. The green corresponding to 5-year student entry, while the red corresponds to 6-year net. And then we have this y-axis to the left that goes vertical that tells us the number of students, right? And the number of students is that variable that is being measured. How many students really is that question, and that bar chart will show us how many students. So what's the data, right? I talked about data before, but data is just the information values that comprise the main part of the graph. The data can provide the readers with a justified conclusion, right? I can see that the data is all this important information, all this important values in the middle, right? The things being measured, the independent, dependent variables. From here, I can make conclusions. I can say that that this that the that it looked like that the length and diameter are for 150 are about the same. I can make that sort of justification, right? Those two reds look the same. Or I can say the diameter for that 600 is the highest, right? Those justifications, conclusions I can make from the data. Right. Now we can look at all the parts together, right? The title, right? That title in front. The expenditure per pupil, which is a student, an average daily attendance, selected years 1977 to 78 through 2002 to 03, right? That's the title. Now we have that other main important part, the data, the information right in the middle, okay, that tells us, our points being measured. It's the information we took. Then to the right, we can see the legend, right? Blue corresponds to total expenditure in unadjusted dollars and total expenditure in constant 2004 to 2005 dollars. And orange, and you can see if we didn't have that, we won't know what that orange and blue lines stand for. So it just helps us give a little bit more data. We have school year at the bottom, which is the x-axis. We have the expenditure per student, thousands, that's the y-axis, right? Those dependent versus independent variables. And at the bottom, we have the NCES Common Core Data CCD 2004-2005, and that would be our source, right? And some other things to watch out for are units. Both the x-axis and the y-axis need to display units, right? Units go there, units are there, right? The y-axis units are thousands of dollars, while the x-axis is thousands. It's important. If you just put that in parentheses, then it corresponds to each data, and then that's okay. That's all you have to do. Instead of, for that y-axis saying 10,000, 20,000, 25,000, 30,000, 40,000, 50,000, 60,000. We just do 10, 20, 25, 30, 40, 40, 50, 60. Those thousands are perfectly fine. Other things to watch out for. Watch out for the intervals. The space, which is the space between each variable. Sometimes it's important to make sure that they have equal spacing or that they fill up the entire graph, right? And we can even look at this picture to the right. It's the same data, but the left just looks way better than the right because there's more data points. It's more visually appealing, a better way to depict the information. That way we're not skewing the information. Right, we're being as specific as possible with our age groups. That's equal size intervals are important. So if we go by every 10 years, that shows a little bit more balance, a little more data we can interpret, while that 40 is a little more bad with the not even size intervals. So what are rows? Rows are the horizontal data series in the table. So it's similar to the x-axis, right? And we can see that those rows go up and down basically. Those rows go left to right, while a column goes up and down. The columns are the vertical data series in a table. Right, so that picture shows us both the column and the row, and that intersection for the column and row. Right, so that row is forward going left to right, that horizontal data series, while the column is vertical up and down, north and south. So rows and column titles, the description given for the row or column, and we can see that picture over at the bottom showing us those titles, right? We have countries, those names for the countries, Russia, Canada, China, USA, so on. And then, those would be the row titles, while the column titles would be territory, land, water, and those would be those column titles. And over to the right, we can see a better illustration of a column, a row, and a cell, which is just one block of information. So let's look at the different types of graphs and tables. A bar graph. A bar graph shows data using bars for specific data for specific x-axis. They can be either horizontal or vertical. Right here, we can just see these are really easy just to understand, right? Bar graph, use bars. A histogram, it's a little more complicated just because of the name. You can't just decipher based upon its name. But the histographs are specialized types of bar graphs where the data is continuous. The bars are touching each other, right? That's just a little bit easier. The bars are touching each other here. Pictogram, all right, think of a picture. A pictogram is a graph that uses pictures to display the data, right? And we have, pictures here to represent the data, right? Uh, the number of children who choose it um, are right there, and the data is represented by pictures of fruit. Block graphs are shown with simple units of data in a fashion of blocks like rectangles or squares. So we have those Roman numerals, data in those blocks. We have even those bar chart looking graphs and that have block squares, and we can just call those block graphs. Pie charts, very simple. Think of a pizza pie. Think of any pie, apple pie, cherry pie, right? Pie charts use pie slices to display data, aka circle graphs, right? And it's just a pie looking graph. A line graph uh, whose segment lines to connect points either at times passes or as the x-axis changes, and we see that, right? They're lines connected by different data points. Now, a Cartesian graph is a little more complicated. They use x coordinates and y coordinates to show how far up and how long a specific point's location is from the origin rectangle points. Right. So if we say 2 comma 3 with parentheses. That means we're going 2 out to the right and 3 up. Um, right, that first x coordinate, if it's positive, we go to the right. If it's negative, we go to the left. And if that second point is positive, we go up. And if it's negative, we go down. And we can see those different points. Right, so if we look at negative 3, 1, it's negative, so we go out 3 to the left from the origin, which is 0 comma 0. We go up 1. Right, and this origin is important to understand because the origin is in two-dimensional graphs where the x-axis intersects the y-axis. This is a point 0 comma 0, right? And we use this term all the time to describe these rectangle coordinates. We'll say we want to go 3 out to the right, 2 up, right? Our point is 3 comma 2, so we go 2 out to the right and up 2. This is a little more complex, but if you just want to know, you do not have to know this right now, but polar graphs are plotted by a radius of a function in the angle theta. A scatter plot is a scatter plot which shows the relationship of data points various through points, right? Scatter plots, points that are scattered. Line of best fit. A line of best fit is a straight line that best represents the data on a scatter point, which is that orange line right there, just to help visualize it better. So interpreting graphs and tables. Right, let's look at question 1. Right, this is a burger question. What day were the most cheeseburgers sold? Well, we have to now look at every day for the cheeseburgers and see which one had the most. And we can see that that day is Saturday. Number 2, what day were the most hamburgers sold? Now we have to go to the hamburger column and look at each row to see which one's the biggest. And that would be on Sunday. Now, what day were the most burgers sold? Well, we have to now look at hamburgers and cheeseburgers. And we can figure out that that would also be Saturday because of 111 and 112 right there. So let's look at another part of this burger question. What day were the least cheeseburgers sold? Well, we gotta go to the cheeseburger column and find the lowest row. That would be on Tuesday at 70. What day were the least hamburgers sold? Right. So now we gotta go to the hamburger column and find the lowest row, and that would be on Wednesday. Now, what day were the least burgers sold in all? Well, that would be on Wednesday, and that would be where it's 74 and 71. Burger question 3, how many more days were the cheeseburger sales higher than the hamburger sales? So we have to compare now each cheeseburger sale to hamburger sale, right? And the answer is one day on Saturday when it's one cheeseburger higher than that hamburger. Oh, sorry. How many days were the hamburger sales above 85? Well, we look at all hamburger sales and we just want to find when they're above 85, and that would be 3 days: Sunday, Friday, Saturday. And was the average number of cheeseburger sales? This is a little bit more complex, so I'll give you the answer here. Um, it's all the cheeseburgers added up divided by the number, which is 7. So it's between 83 and 84. So let's look at another question. Oh, but we can't see the question. Excuse me for a second. I apologize. Um, well, I guess the answers are going to be given for this one. I do apologize. We can still look at it together. How many more delegates does candidate one have than candidate two? And that answer would be, well, we look at candidate two, and we see that candidate two has about 600, and candidate one has about 800. So 800 minus 600 is 200. We can then look at question two. How many does candidate three and four have more delegates than candidate one? And we can see the answer is no, because candidate three is about 300 and candidate four has about 200. So that's 500 in all. And candidate one has 800. So 500 is less than 800. And how many more delegates does candidate one and three have over two? Well, we know that candidate one has 800 and candidate three has about 300, so that's 1100. And candidate two has 600, so that would be 1100 minus 600, which is 500. I do apologize for that mishap. Let's look at another set. How many delegates are there in all? Well, we just have to count up all the delegates, and that would be 1900, because we counted all the delegates that are there. 200 plus 300 plus 600 plus 800, which is 1900. And I don't care so much as you get the answer correct every time, as long as you understand how we get to that answer. Um, how many more votes does candidate 2, 3, and 4 have over 1? Well, candidate 2 has 600 votes, candidate 3 and 4 have 500 in all, so that's 1100 minus 800, which is 300. But in a little bit more complex one, if it takes candidate 4 one day to get 100 delegates, then will candidate 4 reach 800? Candidate 4 is already at 200, so it only needs 600 more votes to get to 800. So that means it will need 6 days to get there. Population question, right? What period had the fastest rate? So what period went from the lowest to the highest? And we can see that's from 1960 to 1970, right? In that blue. What period had the slowest? Well, the one that barely changed. 1930 to 1940, right there, that flat line. And when was the population lowest? Would be when the y-axis is the lowest, which would be in 1920, when the population was 250,000 people. And we can see that right there. Population question part 2. What is the highest population? Well, we just have to find the highest number, which is 800,000 people in 1980. And we can see that right there in the blue. How much did the population increase over the entire time period? So we got to subtract the top from the bottom, and we can find that it's approximately 500,000 people, 500,000 people. And lastly, what time period is relatively constant? And that period is between 1930 and 1950. Where it's pretty flatline, where it's pretty constant. There's not much change going on. Part 3 of this population question: how much did the population grow from 1950 to 1970? So we have to find the value at 1950, find the value at 1970, and find that's 350,000 people right? If we say that's about 700,000 for 1970 and about 350,000 for 1950, we subtract the two and it's 350,000. How much did the population decrease from 1910 to 1920? We know at 1910 it was 300,000 and went to 250,000. So that's about 50,000 decrease. What time was the population approximately 800,000 people? We just need to find when it was 800,000 people, and that was in 1980 at that very last data point. So let's look at paycheck one. How much of John's paycheck goes to hobbies and entertainment? Well, entertainment is 25% and hobbies is 15. So 25 plus 15 is 40%. How much of John's paycheck goes to car and bike repair and in the bank? Well, car and bike repair is 20%. In the bank is another 20. 20 plus 20 is 40%. We can see those two triangles there. And how much more percent of John's paycheck goes to his entertainment and school business and school supplies? Then school supplies, excuse me. Well, entertainment is 25, school supplies is 10. So 25 minus 10 is 15. And we can see those two triangles right there. We can look at another paycheck question. Oh, this is a duplicate slide. I do apologize for that. All right, name all the ways he gets 20%. Well, 20% is car and bike, in the bank, and in the bank, car and bike repair, missed items, and school supplies. We can add those two 10% together. And we can see all those triangles corresponding there. And we have named the two pairs of identical percentages, which is in the bank and car and bike repairs. And what group would be equal to supplies and his hobbies, which would be that entertainment, which is already in the blue. So we can look at another one. We have a couple of these. If I'm going too quickly, just slow down the video and try it on your own. If I study for 3.5 hours, what is my test score? Well, we go to that 3.5 hour mark. See, that's about 71. And that would be our answer, right? That in that blue. If I got an 81, how long did I study for? Well, we gotta go to that 81 marker, and we can see that's about 5.5 hours, right? We can see that right there. And if I got an 85, how long did I study for? Well, I probably studied for about 6 hours, and we can see that trend line forming. If I studied almost 7 hours, what was my score? Well, almost 7, so a little under 7, so about 87, 88. We have that data point right there. What are the different possible times I could study for if I got a 60? Well, there's 3 different times, 1 hour, 1.5 hours, and 2 hours with those data points right there. If I studied for 2 hours, what 2 scores could I have received? And it would have been either 61 or 65 with those data points there, right? And if we wanted to create a line of regression, that line would be something like this for those data points. Not a perfect line, but it's a pretty close line. Have some data points going straight through. Have some. We should have an equal number of going below than above the graph. So it's about a good line. Music question. If I spent 60 minutes listening to music, what could be my math score? Well, we go to that 60 number at the bottom and we go up and we see that my two scores could have either been a 60 or a 90. If I spent 30 minutes listening to music, what is my math score? So we gotta go down to that 30-minute, go up to where it's that point, and that point's at 80 right there. If I got 70 on my math test, what could have been the time I listened to music? Well, there's 2 points that are exactly at 70, either at 45 minutes or 195 minutes. And those two data points are right there. Another music question is, if I got 100 on my math test, how long did I study for? Well, there's only 1 point at 100, and that's at the 90-minute mark right there. And can a line of best fit be made, right? And you would think no at first, these data points are so far apart, but they actually can be. The data shows a scatter plot, so a line can always be made, and we normally want the points closer together, but just try your best in that estimation. And that would be my line of best fit for that data in red. An ice cream question. What are the two highest ice cream preferences and their votes? Well, that would be cherry and cocoa at 7, right there and there. We can also look at what are the two lowest ice cream percentages, preferences and their votes. And that would be vanilla and pecan at 3, right there and there. And what would the two middle be? Well, it's the only two we haven't used yet. That would be mango and berry, mango corresponding to 5 and berry to 6. And those two graphs, and those two bar charts. Assuming no one voted twice, how many votes are there in all? So we just have to count cherry, vanilla, cocoa, mango, pecan, berries votes. So 7 plus 3 plus 7 plus 5 plus 3 plus 6 is 31 votes in all, right? What's the difference between the votes of cherry and cocoa versus vanilla? So we gotta find the cherry. We have to find cherry and cocoa. Cherry is 7, cocoa's also 7, so that's 14 in all, subtracted by the vanilla, which is 3. So that should actually be 11 votes. My apologies. I must have just done cherry and cocoa and forgot to subtract vanilla, and I do apologize on that. What is the difference between votes between mango and pecan versus berry? And that would be 2 votes as well. We just subtract the mango and pecan versus berry. Favorite subject, what's its favorite subject and its votes? Well, favorite subject here is reading by 10 votes. What's the least favorite subject? So the least number of votes, which is science at 4 votes. And what subject received half the votes of reading? So reading got 10 votes. History must have gotten 5 then, right there. What subject has twice the amount of votes as science? Well, science has 4 votes, so we're looking for one that has 8 votes, and we see that art has 8 votes, so that must be the answer. Assuming that no one voted twice, what are the total number of votes? So we just have to count all the votes up, history being 5, reading 10, art 8, science 4, math 6, and together that equals 33 votes. And finally, what's the difference of votes between art and reading versus math and science? Well, we can see that art has 8 and reading has 10, so it's 18, subtracted by math having 6 and science having 4. So our answer would be 8 votes, and we can see those two things being subtracted. This is a gas money question. What year was the gas money the lowest and what was its value? Right there you can see the answer being in 2001 when it was approximately 1.1 $1.10 dollar and dime. What year was gas money the highest and what was its value? Well, we can see that was in 2006 at $3.25 all the way up the top. And if we want to know the difference from when it started, it would be approximately $1.45. That top value subtracted by that lower value. That value at approximately 3 and that value at approximately $1.50. So we can look at a little bit more specific, a little bit more complex, right? What's the difference in cost between 2003 and 2002 and 2003, excuse me. Uh, and we get about 50 cents as our answer. If we look at those two data points, we can see the start and the end there. Oh, sorry. What's the difference in cost between 2000 and 2002? Well, at 2000, it was about $1.50, and in 2002, it was about about $1.50. So it's uh, shrunk, it decreased its negative value of 0.05 cents, 5 cents. What year did it grow the most? And we can see that year is from 2006, that increase in that year. We can look at a quick push-ups question. I believe this is the last one. What day were the push-ups lowest and what was its value? Well, we just see what lowest push-up number it was, and that's on Friday when it was 0. What days were the push-ups highest and what was its values? Well, this was 2 days on Sunday and Tuesday at 25. And what days were the push-ups 15? The push-ups were 15 on Monday. Which days were the push-ups below 11? So we have to look. Those are 3 days, Wednesday to Friday. What are the total number of push-ups? We just count all the push-ups. So it's 105 push-ups. And what's the difference in push-ups on days of Sunday to Wednesday? And that would be 20 push-ups. One more, I apologize, a temperature question. How many days was it sunny for? So we look at that sunny chart on the left, see it's sunny for approximately 7 days. How many days was it rainy, cloudy, and windy? Well, we have to add rainy, which is corresponding to about 4, cloudy, which corresponds to about 2, and windy, which corresponds to about 1. So it's also about 7 days. And what's the difference in temperature on day 1? So now we have to look at the graph on the right, and we see temperature is about a high of 70 and a low of 50, so about 20 degrees Fahrenheit. Another question about temperature: if it was cloudy for days when it was high, when the high temperature was 70, what days would it be? Right, and we know that cloudy can only be on 2 days, and we know that when the temperature high was at 70, so it's about 70 on day 1 and day 5, right? So that's a little two graph interpretation. We have to realize that it's cloudy for 2 days, um, and those 2 days would be 70s. If it was windy for the day when the low temperature was 65, what day would it be? Um, we just have to find when that low temperature was about 65, and that was on day 9. And what's the difference of temperature on day 14? Well, day 14 you can see is about 20 degrees, sort of how it started, about about 80 minus 60. So we can look at graph of a function, family functions. A graph of a function can show functions f of x equaling y, where normally the input is a x coordinate and the output is a y coordinate. So we can determine if it is a graph by the vertical line test to determine whether a graph is a function by seeing if there are multiple y coordinates for every x coordinate. And we can see down below one that is a function and the two that aren't a function because there is multiple or x coordinate. Excuse me, there are multiple y coordinates for that same x coordinate. Asymptotes are lines of functions that approach the function as it approaches infinity. It acts like a barrier. So we can see those horizontal asymptotes, that vertical asymptotes, and oblique asymptotes. So the different types. A polynomial contains either addition or subtraction in their function. That's just a general term to describe a function. And we can look at also linear functions that have their highest exponent to a degree of 1. Common formulas for this is y equals mx plus b, or y minus y1 equals m times the quantity of x minus x1. And the m corresponds to the slope. The b would correspond to the y-intercept, and y1 and x1 are coordinates of a point on the line. Either formula will give you the same answer. Will give you the same line. The quadratic functions are polynomials with the exponent degree of 2. That common formula is ax squared plus bx plus c, right? That x squared. And we can see different types of quadratic functions there. Cubic functions are polynomials that have an exponent degree of 3. 4x to the third, that 4x cubed shows that it's array of a cubic function will intersect that x-axis 3 different times. A rational reciprocal function have a variable in the denominator. For example, f of x equals 1 over x. So you can see that symmetry in those different graphs that are formed. Rational squared or reciprocal is just that 1 over x squared, a little bit different because now they're both positive. Absolute values, an absolute function has a sign creating a V-shaped looking graph. Absolute function graphs have a vertex, right? That origin for the blue one has that graph vertex at the origin, and you can see those V-shaped graphs. The horizontal lines are constant. The function equals a constant value. It's a straight horizontal line. A square root function has the highest exponent at 1/2 and has a curve shape, and will can see that decreasing rate at which it becomes and that flat line eventually. And cubic root function has the highest exponent value of 1/3, and this can be negative. So we can see those two different directions while the square root was only positive. And those are all the graphs. So I just want to thank everyone for watching this video. My name is Aiden Silverman, and I live in Baltimore, Maryland. I'm a junior at Boys Latin. I love to play sports, especially soccer and lacrosse. If I went too fast during the video, please pause the video, go back and slow it down. And these are also some of the sites I used. I hope you enjoyed the video. Thank you for all watching.